rational expressions are things of this form. R of x, rational, of course, is some fraction made out of polynomials. So your numerator and denominator are polynomials. That's called a rational expression. So some examples, some very simple examples are things like this. All of these count. So I know 1 and 2 don't necessarily look like polynomials, but they are. They're just polynomials that only have one term, and it's the constant term. So that still counts. This is more obviously a polynomial. And we're not going to worry about how to graph these kind of in general, but I do want to show you something on the graph what they look like. So let me pop over to Desmos where I've got this stuff graphed. Let me zoom in a little bit. All right, so if you recall, we learned how to graph 1 over x, right? Looks like this. It's your basic rational expression. It's the most basic of your rational expressions. And then transformations like this, where I've multiplied the whole thing by 2, right? 1 over x times 2 is 2 over x. That just multiplies the y values by 2. So you get something that looks like this, right? So where this was 1 right here, this 1, 1 was on this graph. Well, 1, 2 is going to be on that graph, right? So all we did was multiply by 2. So the point I'm making here is that all the stuff we learned about graph shifting, right, adding stuff or adding stuff inside inside or outside the function still applies. It all still works. So, for instance, here's 2 over x, right, that one that we were just looking at. If I change this x into x minus 3, so what I've really done is I have replaced x with x minus 3. I have subtracted 3 inside the function, so I'm expecting this to move 3 units to the right. And lo and behold, it does, right? So you can see that from here, 1, 2 is on this graph, so 4, 2 is going to be on this graph, right? So we moved it 3 to the right by replacing x with x minus 3. Now, there are some things that are not particularly obvious. So this gets a little more complicated than polynomials or kind of other graph shifting, because you can replace things in the top and bottom, right? There's often several variables, or not several variables, but like the same variable, but several instances of it in rational expressions. So something like this, x over x plus 1, and it's not apparent on first glance what's going to happen there. So I will just say that you can figure out what's going to happen here, but it takes a little more advanced techniques than we're going to go into in this class. So don't worry too much about that. That's why we're not worrying about graphing these so much. I just wanted to let you know that it's not always apparent how these are going to look when you graph them. And so probably use a calculator most of the time when you're doing your graphing. Okay. Now, the thing I want to make a point about is the following. So here's your kind of your basic rational expression. This is one of the ones that I had on the whiteboard. And it looks like this. Ooh, that's not what it looks like. It actually looks like this, right? It comes in 2 pieces. And I wanted to point a couple of things out about this and about other ones, right? So every one of these, you might notice, has a vertical asymptote. This one is at 3, right? If I have x equals 3, right? There's an asymptote there. Let's dot that guy up and make it like a 0.5 opacity, right? So there's a vertical asymptote there, and the reason there is a vertical asymptote there is that when I try to put 3 into the denominator, I get 0. And a thing that when you're dividing by smaller and smaller numbers, the number that you are dividing gets bigger and bigger. So for instance, here, let's do this. Let me just do this. So let's say I have number 4, and I'm going to divide it by 2, right? So 4 over 2 is 2. That's pretty straightforward. What if I divide it by something smaller, like 1? Well, I'll get a bigger number out. Okay, well, what if I divide that by something even smaller, like a half? I got a bigger number out. What even smaller, right? So by a quarter, now I'm getting 16 out. What if I divided it by like that, right? So something really, really small, I get out something really, really big. So because this x minus 3 is in the denominator here, when x is very close to 3, the result of this is huge, or negative. It could be negative, right? If this is like, instead of 3.01, it's 2.99, right? Then this thing would be negative, which is why it's going down here. So I can't put in 3, because when I try to divide by 0, undefined, right? Dividing by 0 does not work. So I can't put in 3 into this. So that means that 3 is not in the domain of this function right here. However, it's not immediately obvious from looking at this, but there are times when you can get something weird happening, which is, so notice this, x squared minus 3x plus 2 over x minus 3 versus x squared minus 3x plus 2 over x minus 2, right? Almost the same, but this 3 has turned into a 2. It's a line all of a sudden. And you might ask yourself, why? What? How is this a line? And we're going to see that in just a second. So let me zoom in here just a little bit and show you that it's not quite a line. It's almost a line, but it's not defined at x equals 2. So this thing is almost a line, except, oh, I'm sorry, I gotta turn that off. Oh, at 2. I'm looking at 3. Sorry. I was like, wait a minute, why is this working? I apologize. At 2, it is undefined because that 2 still goes into the denominator and makes it 0. So here we're going to figure out how you can determine whether your rational expression is something like this or something like this. Right, that's what we're going to figure out right now. So the first thing we have to talk about is, number one, how do you figure out where your vertical asymptotes are? And that's actually pretty straightforward. And then 2, how do you figure out when you've got these different kinds of rational expressions? Because this line here is still the graph of a rational expression, but it's a little bit different than the other one. So let's go back and look at my examples. Nope, that's not it. You don't need that. You need, hello, we need to go to whiteboard. There we go. All right, so there's 2 things that we're going to talk about today. 1, finding the domain, which is the first thing I was talking about. And then 2, simplifying, which is, that's how we're going to tell if something is a normal looking rational expression with all the bends and the vertical asymptotes, or if it's a line. So the point I want to make is you want to find the domain first and then simplify second, and I'll show you why in just a second. So here's how to find the domain. So this is where we're going to figure out where the function's not defined and where you've got a vertical asymptote, or possibly just a hole, which we'll see in just a second. So if I want to find the domain of this thing, remember, the only thing that can really go wrong here, we've got basically 2, I guess we've got 3 things that basically can be problems with domain. We've got the negative under a square root, we've got 0 in the denominator, and our new one from the last topic is you could try and take the log of a negative number, which we're going to completely ignore for now. So right now, just think about 0 in the denominator is a domain problem, right? Because then you're trying to divide by 0, so that's no good. So what you do is you figure out where the denominator is 0, but like that's actually how you find the domain here. So the way I'm going to find the domain is I'm just going to take my denominator and set it to 0. So that thing right there. So I'm going to say that I want x minus 3 can't be 0. So x can't be 3. So my domain, everything but 3. That's the only problem we have. All reals. Numbers except 3. There you go. No problem. Same thing when it's more complicated, right? Notice that I'm 100% ignoring the top when I'm finding the domain. I'm not using the top at all. I'm still just going to take this thing right here, set it to 0, x minus 2, or set it to not 0, I guess. So x is not equal to 2. And then the domain, I'm going to write this one in interval notation. I just think it's a little bit shorter. My domain is minus infinity up to 2, union with 2 to infinity. Whoop, shoot. I wonder if that changed my picture in the video. There we go. That's what I'm going for. Yeah, so notice this is the same thing as all real numbers except for 2. That's how you find domain. Sometimes it's a little bit harder. So one of the things that you're going to find with rational expressions is that there is an absolute metric ton of factoring. Very often, rational expression problems start by saying, factor these like 6 polynomials, and that's step 1. So there's going to be a lot of factoring in these cases. So I'll do an example where we're going to find domain factoring. I think I've got that on the next page. Is that right? Yeah, we're going to do some of those in just a second. But for right now, just know that what you're doing to find the domain is you want to set the denominator to 0. That's it. Set the denominator to 0 and then solve, I should say. And that's it. That's how you find the domain. There's nothing else to it. You ignore the top. It does nothing. And notice that when I had 2 over x minus 3, we had the domain was all real numbers except 3, x not equal to 3. So when I go back and look at Desmos, that was this guy right here. Let's turn these off for a second. You might notice that x equals 3. That's where the vertical asymptote was, right? That's the thing that it can't pass. And so, yeah, that's it. That's how you find the domain. All right. Now, here's how you can tell the difference between something that looks like what we just saw, or else something that looks totally different, something that looks like just a line, which we'll do in just a second here. And the way you can tell the difference is by when stuff cancels out. So what we want to do is I want to simplify this. So firstly, I'm going to find the domain here, and then I'm going to cancel anything that cancels. And that's the order you always want to do this in. That's why I wrote this on the first page. Right? You want to find the domain first and then simplify, because you don't want to cancel off the stuff that would make your denominator 0, because it's still not in the domain. So here's what I'm going to do. So the first thing we're going to do here is we're going to factor the bottom, and I'm going to notice that the bottom is a difference of squares. So I'm going to use my difference of squares formula. It's y plus 4, y minus 4. So now my bottom is y plus 4, y minus 4. So my domain, I gotta do it up here, is all real numbers, which I'm just going to write as the R if you don't mind, except for 4 and negative 4, right? So 4 would make this term right here 0, or this factor right here 0, and negative 4 would make this factor 0. So I'm just going to write that as plus or minus 4. So you could write it as 4 comma negative 4 if you want, but basically everything except for 4 and negative 4. And you might say to yourself, well, wait a minute, if it has 2 vertical asymptotes, how does it do with that like bendy thing? Wouldn't it have like 2 spots and be broken into 3 pieces? The answer is yes, it would. Although this one won't, because stuff cancels, right? So there we go. You can see the things that are alike. We're going to cancel those, cancel, cancel. So then this is the same thing as 1 over y minus 4. And I say that, but that's not precisely true. So let's go look. I'm going to use x's in Desmos, but let's go look at this in Desmos and see what it looks like, right? So Desmos, where are you at? So let's turn everything off and go to do this. Let's say we've got I need a new one. We've got x plus 4, x plus 4. If I say y, Desmos is going to think I mean the y-axis, over x squared minus 16. Right, that's what we have. And that one looks pretty much like you'd expect, right? It looks like 1 over x, but it's been shifted 4 to the right, because when we simplified, we had this, right? So it ended up looking like this because we canceled. So this looks pretty much the same as you'd expect, right? It's 1 over x except moved 4 to the right. So let's look at this though. If I did 1 over x minus 4, right? Sure, it looks the same, but if I went to negative 4, right, which is not in the domain of this guy. Oop, that's the wrong direction. Let's try this. If I went to negative 4 here, you can't see it on the graph, all right, until you mouse right over it, right? So it's undefined there. So there's actually a hole there. There's a hole in the graph. And when you're graphing these, you want to actually do what it looks like here and put a little hole there where it's not defined. We're not going to be graphing those. I'm just letting you know that for your next class. But there's not a vertical asymptote here because the factor that is contributing this hole canceled, right? So these two things right here are basically the same, except at exactly this one point, right? So they're almost the same. So if we want to be super pedantic and precise about it, which, you know, it's a math class, maybe we should. what I really should do is this. I shouldn't say those things are equal. I should say they're approximately equal, right? I should be saying this, that those are almost the same, except at exactly x, or in this case, y equals -4, where there's an extra hole in this one, but not that one, right? So they're very, very close to each other, but not precisely the same. However, let me show you what happens. So if this was just like y over y squared minus 16, right, instead of y plus 4. Do that. Show that one. It looks very different, right? It looks pretty much the same here, but lo and behold, it is in 3 pieces, right? So you can see that there are vertical asymptotes here at all the zeros in the denominator, all the things that make the denominator 0, which, by the way, those are called zeros, in case you're wondering. I would say that x squared minus 16 has 2 zeros, one at 4 and one at -4, because there are 2 things that make it 0. Yeah, and so that does not look anything like this, or it looks very different, I should say, right? It has some superficial similarities. Okay, so that's how you can tell when you're going to get something that is a little bit different, is when things cancel. So for instance, the reason this one and this one look very different is because, well, I think I hope I have it on my next page here. I'll do this one in just a second, just as another example. Oh, I don't. All right, so if I had this x squared minus 3x plus 2 over, it was x minus 2 versus x minus 3. Well, when I factor the top, I end up with this, x squared minus 3x, excuse me, I didn't factor anything there. Let's try that again. When I factor the top, and actually factor it this time, I get x minus 2, x minus 1. And this one is x minus 2 in the denominator. So when I cancel these, the thing I'm left with is just x minus 1. So that's why it looks like a line. It looks like the line y equals x minus 1, because at every point except for exactly x equals 2, these 2 things are the same. So like this and this are almost the same except for at x equals 2, where this is not defined, but this is totally fine. You could put 2 into this, no problem, but you can't put 2 into this, even though they're very, very similar to each other. So that's how you tell the difference, is when things cancel out, you get different looking rational expressions, or you get different looking graphs of rational expressions, I should say. However, the fact that the x minus 2 cancels out of this doesn't mean that that 2 is in the domain. You still can't put 2 into this. You just get 0 over 0, which is still undefined, right? So that's why you have to find the domain first and simplify second, right? So you can figure out what the domain is before you cancel off the stuff that is impacting your domain. All right, so let me do one more example of simplifying here. So this is, well, it's time to try and remember, or try and remember everything that you learned from factoring. So these are a couple of special factoring formulas. Notice that my top here is a difference of squares, right? So let me, I'm going to rewrite this. This is 2t quantity squared minus 3 quantity squared. And the denominator is 2t quantity cubed. That's a cube, believe it or not. Let's try rewriting that so it's readable. Cubed. All right, that's almost readable. Plus 3 cubed. Oh, that's a much nicer 3. So now I'm not saying you can cancel the 2 t's here. I just wanted to remind you that what we've got here is difference of squares over sum of cubes. And so you got to use your formulas. So I will let you look up the formulas. I remember them, of course, so I'm just going to use them. So this is going to be 2t plus 3 times 2t minus 3. And then the denominator is going to be 2t plus 3 times 4t squared minus 6t plus 9. And by the way, you might be tempted to look at this thing right here and say to yourself, ooh, I bet I can factor that, right? The 4t squared and the 9 are both squares. I bet this factors the perfect square. And that's really tempting to think that it does, but it doesn't. This actually never factors. When you're doing the sum or difference of cubes, this term right here, the one with three things in it, or this factor, I should say, the one with three terms in it, it never factors. So this is as reduced as this is going to get. And so we cancel the 2t minus 3's, and I'm left with this. So that's for simplifying. If I wanted to find the domain, I would set this to 0 and set this to 0. In fact, let me go do that, right? So yeah, let's just make a new thing and go do that. I'm going to start over from the beginning just to refactor it. So I'm going to have 8t cubed plus 27, and that's going to be 2t plus 3 times 4t squared minus 6t plus 9. Is how that factors. And so what I'm going to do is set this equal to 0, equals 0. And then I'm going to use the zero product property. The zero product property tells me that I have two things, this and this, that are multiplied together and giving me 0. So I can set them each individually to 0. So I can say that 2t plus 3 equals 0, or 4t squared minus 6t plus 9 equals 0. Now, the first one is much easier, and this is actually why factoring is so nice. The first one's much easier. I can just subtract 3, divide by 2, and get t equals -3/2. The one on the right, though, I told you it doesn't factor, but that doesn't mean we can't solve it. We can still solve that equation. We just have to use the quadratic formula or completing the square. So that's what I'm going to do. I'm going to use the quadratic formula and say that t is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. And so I'm going to get t is 6 plus or minus the square root of 36 minus 144 all over 8. And I think you can see the problem here, right? This number is negative, and I'm trying to take the square root of it. So the only solutions here are complex numbers. So no real solutions to this. So no real t's. Well, okay, there's one real t's, no more real t's. Okay. Right, so there's only the one. Now, one thing that's nice here is, I'll just tell you this, and then you never have to do this thing I just did. When you factor a sum or difference of cubes, not only will this never factor, it'll also never have real solutions. So you actually don't even have to worry about this. The only real solutions you will ever get from a sum of cubes or difference of cubes is the one associated with the first factor. You don't even have to worry about this one. If you're interested in why that is, I'll be happy to show you at some point, but we don't need to go into it in this video, but it is true. Yeah, and so that's how you simplify and find your domain. So my domain is that t does not equal -3/2. So that is this. So we have domain r r except t equals -3/2. And then the simplifying leaves us with just this bit, right? When we simplify, that's what we're left with. 2t minus 3 over 4t squared minus 6t plus 9. And you might say to yourself, I bet those things cancel. They don't. They never do. Like I said, we can't factor the 4t squared minus 6t plus 9 anymore, so nothing else cancels. And I do want to point something out. You absolutely positively cannot do this, right? If you have things that are being added or subtracted, you cannot cancel them. It never works. People do this all the time. That is probably the single most common mistake I see people make with rational expressions. They see a 3 and a 9 and think to themselves, aha, 3 goes into 9. I'm going to cancel. Don't do it. The only things you can cancel are things that are multiplied. And the only things being multiplied here are the binomial terms, 2t plus 3 and 2t minus 3. You want to think of this right here as all one piece. So you either cancel all of it or none of it. Same thing with this, right? This 2t plus 3 could cancel because there was another thing exactly like it on the bottom. But the 2t minus 3 can't cancel because there's no 2t minus 3s on the bottom. And like the 2 doesn't cancel with the 4, nothing like that. Just multiplied. So things, only multiplication cancels with division, right? Effectively what you're doing when you do this is you're trying to cancel something that's being subtracted, right? I'm trying to cancel a subtraction of 3 with an addition, or I'm not saying that very well, but I'm trying to cancel addition or subtraction with division, and that it doesn't. Division is not the opposite of addition or subtraction. So you definitely cannot do that. Just don't do it. Only cancel the polynomial things that are multiplied. That's it. And I think that is pretty much all I want to say about finding domain and simplifying rational expressions. So let me go back to my first page. Find your domain first, red, first. Then simplify, second. And in fact, there is a 0th step here, which is, I'm gonna go make a new page. With rational expressions, rule number one of rational expressions. And I'm realizing now I probably should have had a page on this to start. Factor everything. This needs another box. I need a second box to really highlight this. Magenta, that's a nice highlight color. Look at how garish that is. You can't possibly forget something that garish. Factor everything. That's rational expressions. Rule number one, factor everything. If you do this, it makes things so much easier. So you're gonna want to get good at factoring, or this will probably make you good at factoring, to be fair. But yeah, rule number one, factor everything. It becomes very obvious what to do once everything is factored. All the canceling is simple. Yeah, factor everything. Okay, with that admonishment, I'm going to go ahead and stop the video here because I think that's all I wanted to say. So I will see you guys in the next one.